Hello and welcome. I am Dr. Pauline Fu. In this video, I will present inference on least squares regression model. By the end of this lecture, you would be able to state the requirements of least square regression model, compute standard error of estimate, verify that residues are normally distributed, conduct inference on slope of least squares regression model, conduct a confidence interval estimate about the slope of least square regression model. So let's start by the requirements. Requirement 1 for inference on the least squares regression model. For any particular value of explanatory variable x, the mean of the corresponding response in the population depends on that x. So we use mu, then subscript y. X represents the population mean. So mu is the population mean when the value of explanatory variable is x. Some textbooks just simply use mu, okay, without a subscript. So this one is the mu is the mean, okay. So requirement 1, actually the keyword is linearly on x. So mu, linearly on x. That is requirement 1. And requirement 2, the response variables are normally distributed with mean. What is the mean of the response? Remember, response variable is y, okay, is this direction, response variable. Normally distributed with this one as the mean. This is the mean of response variable. Standard deviation is sigma. And what is x again? X is the explanatory variable. This is x. The least squares regression model. We use yi represent least squares regression model. It is beta 1 xi plus beta 0 plus epsilon I. Yi is the value of response variable, means this direction, okay, for the ith individual. Xi is the explanatory variable, so xi is this direction. Beta 0, beta 1 are the parameters to be estimated based on sample data. And epsilon I is random error. This random error has a mean is 0. Standard deviation equal to population standard deviation. The error terms are independent. Okay. So that is the least squares model. Remember, this part actually is the mean, population mean, and plus an error becomes the response variable yi. Now, a new concept, standard error of estimate, SE. This SE formula is you use observed yi is observed value. Yi hat is the predicted value, okay? So actual value minus predicted value, that is the residue by definition, Okay, so by definition, what is residue? Okay. Residue is actual value, yi, or observed value, actual value, minus predicted value. For example, if your actual age is 21 years old, but I may predict your age is 20. So your actual age is 21 years old. I predict based on a model, your age is 20. The difference is the residue. Observed value minus predicted value is the residue. Remember, we have many data, okay, many data. You do the residue for each data, and then you square the residue and add all residue together, divide sample size minus 2, and take square root. That is the standard error of estimate. Standard error for the estimate for a least squares regression model. It is the equivalent of the standard deviation for normal data. If I give you a set of data, you can calculate standard deviation, okay? Here, if I give you two variables, X and Y, you can calculate standard error of the estimate. So now, this is the example to compute the standard error. In this example, we have X. X represents depth at which drilling begins. Okay, so and Y represent time to drill 5 feet in minutes. So anyway, this is X, this column is X, and the second column is Y. And we want to explore the relationship between X, Y. That is the core of this lecture, to explain the relationship between two variables. One is X, the other is Y. And now our task is to calculate the standard error. Standard error. So we need to use the formula. We need to calculate observed Y. So where is the observed Y? Each number here is yi. Each number here is yi, observed Y. And then we need to figure out the predicted Y, yi hat. And how do I get yi hat? You get yi hat usually through the technology. There is a formula in the textbook. You can calculate, you can get yi hat as long as you can get the slope, you can get intercept, you get yi hat. But here, I'm going to use Excel to get yi hat. So this is the data I copied to Excel. Okay, we have X, we have Y. And how do I produce yi hat? You do regression analysis. I'm going to cover this one, okay? So you go to data, and then data analysis. Select regression, click OK. Y input, I will delete original setting so that you see I started everything from scratch. Y setting from here, B1 to B13, that is Y. As you can see, I included labels. X is from A1 to A13, okay? And then output range, I want the output in the same page. Maybe output I will put in maybe D2, okay? Maybe D2, no, I will select the cell. This cell is my output, D3, okay? Then you click OK button. And now you get this output. And based on this output, you will get prediction yi hat. How do you get yi hat? You need two values to get yi hat. One, slope. The second, intercept. And those two values are here. I'm going to highlight. Oops, it is not good. No. So those are, one is the intercept 5.52. The other is the slope 0.0115. Okay. So I'm going to copy this one into OneNote so that I can make a notation. Okay. So I will copy. And then, where should I put the result? Maybe on the side here. And then I try to make this bigger. All right, so you have these two numbers. And these two numbers, one is the slope, 5.52. The other is one is the slope, 0.011. The intercept is 5.5272. Okay, once you have these two numbers, okay, so intercept is obvious, 5.527. And this number, I will use different color. 0.0115, this number is the slope. Okay, once you have intercept, you have the slope. See, you can get y hat. This is y hat. And intercept 5.5273, slope 0.0116 if you round up. Okay, so you get y hat. And remember what is y hat? Y hat is the predicted value for y. Predicted value for y. Okay. All right. See, the formula need y hat. Need y hat. Now, based on observed y and y hat, we need to produce residue. Remember what is residue? Yi minus yi hat, that is residue. So observed minus predicted, that is the residue. Okay. So I'm going to do that in Excel. First, I need to calculate y hat, and then use y minus y hat, get residue, and then square residue, and then add all residue together, divide n minus 1, take square root. That is standard error of estimate. So I'm going to pull out my Excel again. Excel. Yeah. So this is my Excel. Okay. I should insert a column here because I want to do some calculations. So I want to say what is the predicted y. This one is observed y. So observed y, OBS, yeah. Observed y. Okay, this is observed y. Now I'm going to do predicted y. Remember, predicted y is the equation. Okay, so y it is, I want this to the left. Okay, so equal. Okay, based on this equation here. See, slope times x plus intercept. Where is my slope? Remember, this number is my slope. Okay, so this slope times x, this is my x, that is slope times x plus intercept. This number is intercept. Okay, because the slope and the intercept is the same for all the data, so I need to use absolute cell reference. So $F, $19. Okay, and here for cell F20, F is the slope. Slope is the same for all of the data here. So $F, $20. A2, I will keep, it is A2, because A2 next time becomes A3, next time becomes A4. I want A2 to be changed. If you need something to be changed, you use relative reference. If you do not want something to be changed, you want something fixed, absolute cell reference. Okay, so anyway, this is the predicted value for 5.88. 5.88 is the observed value. How do I do predicted value again? Regression equation, see, based on this equation here. Where this equation come from? Coming from these two numbers, intercept and the slope. Okay, so I press enter key and I get a predicted value 5.93. And then you use file handle, copy down. That is the beauty of Excel. Just one calculation, you get all the results. Okay, so for example, this 6.1 is the predicted value of 5.99. Okay, last one, 7.72 is the predicted value of 7.9. Okay, so this column C is predicted Y. Predicted Y is Y hat. Y hat. Okay, so now you have observed Y in column B, predicted Y in column C. You can do residue. Okay. Remember, residue is observed Y minus predicted Y. So 5.88 minus 5.93, that is residue. Okay, you produced a residue. Now do this residue for all the cells. Okay, you get a residue, and I need another column. Now you need a residue square. You need to square residue. Okay, so equal this number square. Okay, oh, what's happened? Okay, way too much decimal. Maybe I don't need those too much decimal. No, decrease decimal. Okay, so this is residue square. So do the residue square for other cells. Okay, so residue square. And remember the formula said, this is residue square. The formula said you have to add them all, sigma. Sigma means add all those squares. Oops, oops, oops. Oops, I want to see the Excel. Oh, this is not my Excel, that is the picture. Okay, this one here. So now I need to add all these values together, sigma. Okay, so Excel sigma is sum, sum of all these numbers. Okay, sum of all these numbers. And you get this number, sigma residue square. And then you have to use this number divide 10 because n is 12, n is 12, 12 minus 2 is 10. So use the sigma square divide 10, okay? And then you have to take square root. See, you have to take square root after you divide 10, take square root, okay? So take square root, SQRT of this number. So this guy is SE, standard error of standard error, okay? Standard deviation for error, okay? So we get this number, okay? What do I do? I want to copy this formula, maybe this one. Okay, so never mind. So this is the standard error we computed using the Excel, okay? And the result we get is, see, this is a calculation here. So the final result we get 0.5197. The same as we got here, see, 0.5197 here. Okay. All right, so that is the standard error of the estimate. Next, we want to do the hypothesis test regarding the slope, beta 1. Remember, we need the two conditions. The sample is a random sample. The residues are normally distributed with constant error variance. Those are the requirements to conduct linear regression. Remember, the least square regression model is this one. Yi is the response variable, x explanatory variable, beta 1 slope, beta 0 intercept, epsilon I random error. Okay. What we want to do, we want to test if this slope beta 1 is 0 or not. And there are three situations. If this is two-tailed test, null hypothesis said slope beta 1 equal to 0. Alternative hypothesis said slope beta 1 not equal to 0. And if it is left-tail test, we say null hypothesis is slope is 0. Alternative hypothesis said slope is less than 0. Slope is less than 0 means the relationship between x and y is downwarding, is something like this. This is xy when you have smaller than, slope smaller than 0. And the next situation, right tail test, alternative hypothesis H1 has slope beta 1 greater than 0. Okay, when you have greater than 0, you have a positive relationship between x and y. Means when you increase x, y also increase. That is greater than 0. Step 2, specify alpha 0.05 or 0.01 or 0.1. Next, we calculate test statistic. Remember, test statistic is just a formula. The formula said, use B1 minus beta 1 divide S then subscript B1, and we call S subscript B1 is the standard error for the slope. Standard error for the slope. Okay, so where is my B1? Remember the Excel. Use different color. Use blue. Where is your B1? The slope, we use B1. B1, maybe I'll use same color. So B1 is the slope, and it is this number here, 0.0115. Okay, that is your B1. And intercept, this number intercept, we call B0 intercept. So you know what is B1, B0. You can get B1, B0 through Excel. Okay, and then there is a number here, standard error. Standard error for slope is this number here, 0.003. That is your S subscript B1, standard error for slope. Okay, standard error for slope, it is 0.00300. Okay, so because the test statistic need B1, need SB1, you can get those two numbers here. Okay, the green one is B1, the blue one is SB1. Okay, so go back to my slide. So we know what is my B1. Okay, so B1 in my example, B1 0.01155, maybe 0.0116. Okay, so 0.0116, that is my B1. SB1 is the number here, 0.0030. 0.0030. Okay, and then you can calculate this B0. Okay, so I will do calculation here since I have those two numbers here. So I will calculate test statistic equal to this number divide this number. Okay, that is my test statistic. It is 3.85. Okay, I'll write down here, test statistic 3.85. Okay, so equal to 3.85. I get test statistic. And then guess what is the next? Use classical approach to figure out the critical value for T. And then compare critical value with the test statistic. Okay, so that is our next steps. So just recall, if you have a two-tailed test, you have two critical values. Okay, the critical value decide rejection region. This is rejection region. This is rejection region. Okay. If you have left tail test, you just have one critical value, and you have this left tail is the rejection region. Okay. All right. So if you have a right tail test, you have one critical value here, and the rejection region is here. Okay. All right. So you need to compare critical value with the test statistic. Okay. If it is two-tailed test, if your test statistic in two-tailed test, if your test statistic is here, reject. If your test statistic is here, reject H0. And if your test statistic is here, do not reject H0. And when you have left tail test, if your test statistic is here, reject H0. If your test statistic is here, do not reject H0. Right tail test, if this is your test statistics, reject H0. If this is your test statistics, do not reject H0. That is what it said in this table. Okay. That is the critical value approach. and p-value approach, and you need to find the p-value. P-value is the area corresponding to test statistic. And where is my test statistic again? 3.85. Okay, so 3.85. And the degree of freedom n minus 2. 12 minus 2 equal to 10 is the degree of freedom. You can use a table to get approximate value of p-value, but using Excel, you can get exact p-value. How? So I'm going to do p-value here. So I'm going to put a result here. Try to increase the font size. So equal, we want to calculate p-value. So t dot dist. This is two-tailed test dot 2t. Okay. X is 3.85. Degree of freedom is 10. Okay, the result will give you the p-value. Okay, so I'm just going to copy this into here. And this result from the Excel 0.0032. And this is the p-value from Excel. Once you get the p-value, compare p-value with alpha. Where is our alpha? Step 2, specify the alpha. Okay. Choose an alpha. We haven't given you the alpha yet, but regardless the alpha 0.05 or 0.05, this p-value is very small. Where I am? I'm here. Okay. P-value approach. Okay, I'm here. Okay, so this is our p-value. This p-value for sure smaller than alpha. Okay, alpha usually it is 0.05 or 0.05 or 0.1. So smaller than. When p-value smaller than alpha, we reject the null hypothesis. Okay, so this is our example. Okay. This is a p-value. When you have two-tailed test, the area corresponding to a test statistic, that is p-value. In our situation, test statistic 3.85 here. Okay, this is 3.85. Okay, and when it is left tail, the area to the left of test statistic is p-value. When you have right tail, the area to the right of the test statistic is the p-value. Okay. So far, we actually gone through the theoretical approach, theoretical part to test if the slope equal to 0 or not. Now we are going to use this data here. Remember, we have X, we have Y, this data. We use this data, okay? To test the claim that there is a linear relationship between dwell depth and dwell time. Okay, remember dwell depth is X and dwell time is Y. Okay, so test the claim there is a linear relationship between X and Y at 0.05 level of significance using the drilling data. That is the question. I actually already did that question because I already calculated test statistic p-value, but here just briefly refresh our memory. Okay. So verify the requirements first. So the experiment is randomized. Okay, so it is the random sample. In the previous example, we know residues are normally distributed by construct a residue normal probability plot. So I'm going to do it now. how do you produce a normal probability plot? Okay, so watch. Normal probability plot, okay, so you go data, and then data analysis, regression, click OK. Okay, Y input B1 to B13 correct, X input A1 to A13 correct. So output range, maybe I will go to the new worksheet. Okay, and I need residue plot, see, residue plot, no, not residue plot. Right now, I need to know the normal probability plot. Okay, so I need to check out, see, normal probability plot. Okay, why do I need normal probability plot? I want to see if the residue are normal. Okay, so you click OK button. See, normal probability plot is here. Okay, and this normal probability plot looks like roughly on the straight line. Okay, so I'm going to copy this one into one note, maybe on the side here. See, this normal probability plot roughly on a straight line. Okay, that means residues are normally distributed. Residues are normally distributed. Okay, so this is satisfied. And we need to verify the requirements. Is this the one? I have to click undo button because. Next, we verify the requirement of constant error variance. Okay, we plot the residue against explanatory variable. Okay, so I'm going to show you how do I know we have a constant error variance. How do I know? You produce residue plot. How do you produce residue plot? Go to Excel. Okay, so this is normal probability plot. You go back to your data. This is my data. Okay, you repeat yourself. Go to data, and then data analysis, regression, click OK. This time you need residue plot, not normal probability plot. Okay, and produce new sheet, click OK button. See, this is the residue plot. This is your residue plot. I'm going to copy, Control C, and paste so that I can do the annotation. Okay, I want to paste it here, maybe here. So this residue plot, you see this residue plot spread out evenly and without any pattern. This is a good residue plot, and we can assume constant variance are hold true. Okay. All right, so far we verified the requirements. Okay. So next, let's use the steps, okay, to do the hypothesis test. So null hypothesis said there is no relationship between X and Y. Remember what is X? Trading depth is X. What is Y? Trading time is Y. No relationship means slope equal to 0, beta 1 equal to 0. And alternative said there is relationship between X and Y, slope not equal to 0. And then use alpha 0.05. Okay, and remember we get B1 equal to slope equal to 0.0116. How do we get this slope? Remember this number, see, this is the slope. Okay, 0.01155 round up becomes 0.0116. That is the slope. Okay, and also we did to determine the standard deviation B1. We know where is the B1. The number beside this slope, that is the B1. I'll use different number color. This is SB1. This is from Excel. But our slide tell you to do calculation for by hand. So that is what I'm going to go to. By hand to determine standard error of B1, we use S, then subscript B1 represent standard error of B1. Okay, so what do we do? You do, this is X. Once you have X, can you do X bar? Of course you can do X bar. And then use each number minus X bar, you get this number. Each number, each X minus X bar, you get this one. And then you square this number. You square the number. After that, you add all this number together. Add all this number together. That is your signal. And you get this number. Okay. And once you get this number, standard error. Once you get this number, we want to show the B1 in the next slide. You use the formula for SB1. You get the SB1. Okay. So what is the SB1? This is the formula for SB1. SB1 equal to SE over square root of sigma. Remember, this is the sigma we get. This number goes to here. By the way, this is the formula for SB1. In this formula, we need SE. Remember, we did SE before. Okay, SE equal to 0.5196. Okay, so you get this number. This is by hand. You get standard error of the slope. This is S subscript B1. And this number is just the number here, the green one. I will make it bigger. Use Excel, you can directly get this number. Okay, this number here. Okay, and once you have SB1, you calculate test statistic. Remember, test statistic is just a formula, B1 over SB1. Okay, B1 is the slope. SB1 we just calculated, and you get test statistic 3.86. And remember, we also get this test statistic from Excel, where this part, this number is the test statistic. I will make it bigger, this purple one. This is test statistic from Excel. See, test T-start. Okay, this is test statistics. All right, so once you have test statistic, using classical approach, you need to get critical value, okay? So how do you get the critical value? You can use the table or use Excel, okay? So I'm going to do critical value here, equal. This is two-tailed test, so critical value is T dot INV dot 2T, okay? And alpha is the probability, 0.05, degree of freedom is 10. See, critical value 2.228, okay? So we get the critical value here, 2.228, okay? Once you get this critical value decide rejection region, okay? Honey, sorry, I'm recording. critical value decide rejection region. Okay, so now locate your test statistic. Your test statistic, remember what is your test statistic? If you forget, go to Excel. 3.85 is your test statistic here. Okay, so 3.85 is here. 3.85. Obviously, test statistic is in the rejection region. So we reject H0. We reject H0. What is my H0 again? H0 said slope equal to 1. We reject H0. Therefore, we are saying conclude slope not equal to 1. Okay. In another word, there is a linear relationship between x and y, or there is linear relationship between dwell depth and dwell time. So that is the classical approach. We conclude there is linear relationship between x and y. Next, p-value approach. Remember, how do we get p-value? You can use the table. When you use table, you get approximate p-value. When you use Excel, you get exact p-value. Okay, so remember what is p-value? P-value is the area corresponding to test statistic. Remember our test statistic is 3.867. Okay, and this area plus this area is a p-value because this is a two-tailed test. These two areas added together is a p-value. Okay. So how do I use Excel to do the p-value? Show you here. Maybe I'll put p-value here. So equal t dot dist dot 2t, opening bracket, x is 3.867, degree of freedom is 10. Okay, so this is the formula. Okay. And the p-value 0.00312. Okay, see, I get this p-value. This is the Excel formula. All right, once you get this p-value, obviously this p-value is smaller than alpha. When p-value is smaller than alpha, reject H0. Same conclusion as we get from classical approach. Okay, so final conclusion, there is sufficient evidence to conclude that a linear relationship exists between dwell depth and dwell time between x and y. All right. So far, we did hypothesis test for the slope. Next, we'll do the confidence interval estimate for the slope of the regression line. Remember, when you construct confidence interval, we need a lower bound, upper bound, and we need the slope B1, we need the critical value T half alpha, and we need the standard error of the estimate. We also need xi minus x bar square, sigma square root. Remember, we already did this calculation. Okay, so we just need to plug in the number to get the confidence interval. Okay, so this is example. Construct 95% confidence interval for the slope of least square regression for the drilling example. Okay, so we get B1 as B1. Where is B1 as B1? We did those by hand. We also did by Excel. See, this is B1, 0.0116, and this is SB1, 0.003. Okay, and then we need to calculate the degree of freedom. I also calculated, remember the critical value, 2.228 for 10 degree of freedom. okay? And then you plug in those numbers. You can get the lower bound and upper bound. And how do you interpret this lower bound, upper bound? We are 95% confident that the mean increase in the time it takes to drill 5 feet of each additional foot of depth at which the drilling begins is between those two numbers. Okay. In summary, I did a hypothesis test for simple linear regression line. So we are testing if the slope of the regression equal to 0 or not. But before we do test, we need to make sure we check the requirements of linear regression. Okay, so sample from randomly selected sample. The residues are independent with each other. The variance for the residues are normally distributed. And also the residue coming from a population which has a normal distribution. Those are the requirements. And then you can use a classical approach or p-value approach to test if the slope equal to 0 or not. Finally, we introduced a confidence interval estimate for the slope. Okay. Hope you learned something from this video. Thank you so much. I'll see you next time.